Free University in the US, and then back to Europe in the ISI Foundation in Turin. Basically, the interest is, well, as you can see from the first transparency, is on networks, compressed networks, on topology, but also on traffic on the web, and also internet. And that's a little bit there. So, and now, well, he's here. He has a contract for 3 years as a high. Okay.
Yes. Well, thank you for the introduction. Well, I mean, actually, I gave a brief seminar here, and I think most of you were also not here. There is something that has changed, which is this part here. As you see, I mean, the symbol of the institution now is different. So I am now here at
the talk is the same? The talk
no,
is the
I could be the same, you want? But actually, there are some further developments of that one too. Now I'm here now, so if you're interested in something, especially the kind of things I'm doing related to networks, I'm more than happy to collaborate with you. Well, so this is the outline of the talk. I'm going to talk, the topic is essentially the internet and traffic on internet. And the outline is, this was done for a kind of heterogeneous environment, no? So I'm not expecting anybody to know about the internet and the web, so I do a sort of introduction to that, and the kind of terminology that I'm going to use later. So then after that I will show you what we understand by navigation traces, and how we measure them, and what they mean, and the kind of data that we are able to collect on this sense. Then once we have the database, I will tell you which is the data analysis that we run on that, the aggregation level. Of course, by the way, all the data is relative to traffic on the web. Huh? So this is what I'm talking about here, about data analysis. And with that, this also at individual level basis, looking how people navigate, and this defines what we call navigation trees. And then I will show you how we model all this process. That's actually, at least I am a physicist by formation. The other guys here are computer scientists. But the process is very similar to what happens for instance, in quantum theory, when you are trying to model the atoms. You start with a simplistic model, and you start to add more and more detail. So this will be the process here at the very end. I will show you first the more simplistic model of navigation on the web, and then I will increase the level of detail when we see in the data that actually does synthesize. Okay, so first of all, the internet. So internet started like this. So now everybody knows that you go to a computer and you get immediately access to all the world. In '69, this was not like that. Actually, the internet was this only. So this was called ARPA, and it was a military-based project. And these are the first 4 nodes. So mostly universities, UCLA, Utah, and San Francisco, and also everything related to military research. Then it started to grow, and it did it very, very fast. This is from the 70s, and I'm going to come here because I think it's easy to look at it. In the 70s, it already included, apart from the original nodes in the West Coast, there were already some more here, and then there started to be some also in the East Coast with MIT and Harvard on board, and in '77, so only 7 years later, or 8 years from the beginning, let's say, this was already something like this. So as you see, many academic institutions have already connection to the internet at that time, and there was even connections to Europe, in London, or here in Hawaii. So it was starting to develop outside the US. Well, the origin of all this was the idea of having distributed information. In the sense that if something happens to a place, and since this were military, they were thinking attacks from nuclear weapons or from some organized things, then the question would be that the information would be able to survive in this distributed environment. Because, someone to end up with the whole thing would have to shut down the full network, so attack all the nodes in the network. of course, it has been used for completely different things. As soon as the internet went away, people started to use it for many, many other things. And actually, what has happened since then until now is that there has been an explosion of systems in the internet. Well, here this is a map of the more or less current internet. I don't remember which is the date of this, but I can show you the next data which have actually date. And it has expanded to all the continents, out of the US and North America towards Europe, and even Africa or South America and Oceania. Well, for the rest statistics, we will have to go very detailed, but the internet today looks like something like this. So it has grown not only in numbers, but also in complication. So it's a map of the autonomous systems. The autonomous systems have the big servers of the internet, and there are around 40,000 in the last census that I remember of. So the number has exploded. And this is a physical network. I mean, we are still speaking about servers and computers connected by cables. No? So this is a physical thing. It's not.
Were you aware that the thing that the internet was scale-free was falsified?
Yes, I know these things. Actually, there's all these discussions about power laws and exact power laws is also something that I usually try to avoid because it's not very clear that those are.
Yeah, because I mean the internet is physically uses more connectivity because the servers can just serve.
Well, I mean the feeds of the
because
the
the
network
picture there looks like a scale-free network.
Well, yeah, because this was normally groups that actually wanted to push that idea, but I know that this is why this tool. I don't know if this will be a power. Okay, so this is about the internet, but what I'm going to tell you is not about this, it's about the thing that actually lives on top of the internet. No? So, and this is the web. Well, everybody knows what it is, I suppose, but this is, this is a browser, and this is a photo of a browser. So people essentially go there and write some URLs to set the direction of the pages, and then you connect and go there to see the information that is contained there. Then the different pages are connected by the hyperlinks, and this generates another structure, which is also a network. This is not a real physical network, so there are no limits, for instance, for the number of pages that you can have, or the number of information that is around. Or at least it's not limited as development, it's more limited by memory problems and probably by transmission of information problems. But this is the kind of structure I'm going to talk about. So. And I don't know if I have a photo. Well, no, I have. This is about the users, but I don't have a photo of the structure. The structure is as complicated as the previous one. But this is essentially the motivation for the users to go to internet. Well, many times in a colloquial way, you say, "I connected to internet," and you are not meaning actually that to go to the physical thing and connect there, just having I don't know, like the ultimate aim actually is to connect. No? So the ultimate aim usually is to navigate on the web and to get information out of that, or now to use these web 2.0 applications like online social networks or many other of these tools of even with people now. And this is, all these tools and all this process have actually generated this. This is an explosion of the number of users. And I wanted to show, this is from this is given by an agency of the UN. The last data correspond, and mostly I think this data correspond to 2007. I have data much recent than this. And what I would like to show here is that, this is the percentage of people using this kind of technology, essentially the web, in the different parts of the world. They are separated in these developed countries, developing world, and the whole world globally. But an important question here is that in the developed countries, at least for 2007, we have this 62% of population already using the web. And even in the developing countries, you can have around 17%. So this leads, I don't know if I have the numbers here now, but I will tell you the numbers by heart. So this leads to something like, in the last census, it was around 2 billion people using internet. 2 billion out of the 6 billion that there is in the world. So that gives you an idea of the kind of access that you can get into the network. No? Of course, that generates a huge number of pages and contents because everybody can produce their own contents. Those at least for the level of domain. So when you write the dot, but it comes afterwards, it's around 10 to the 9. But all those have internal structure, so the number of pages will be several order of magnitudes much bigger than the 10 to the 9. Okay, so this is just to give you an impression of how the thing is. And the problem that we are interested in is actually on how people or the users navigate on top of this platform by pages and hyperlinks. So how they explore the information. This is what I wanted to show you here. So essentially, we have the users on one side, and they are just navigating. This was the usual confirmation of the old network, if you want, of the old web, the first version of the web, because you have the content distributors that were usually companies or very particular users, the only one with power to edit the HTML, which was the previous thing. And essentially, they were just producing this, and the user just looking at it in a direct way. The situation has changed a lot, but unfortunately, I have this slide here, because now, today, we have much more flexible things. Well, I mean, now what happens is that in the Web 2.0, the users are able also to edit the content of the pages, and in that way to communicate between themselves. So if you want to study the new way in which people is navigating, you should actually add more detail here. No? So the possibility of interacting between the users. The models I'm going to show you are for this kind of set, which is the very first thing that you want to actually implement. And it's already, I mean, there are already complications on that, so it's very hard. To make a model with the full thing would be, of course, probably a way to go in the future, but it's more complicated. No? Because then you have interactions between the users. And this change of contents on the other side. And how do you get the information about what people does? Because the question is not only to have models. I mean, that's good, but it's also important to check what happens in the real data, in the real world. Well, the way to do it is based on this. So I call this navigation traces. So what happens is that in this kind of online world, everything gets registered, and that's also a warning. So everything that we do, essentially, I mean, imagine that we have this guy here, and he has his computer and his IP, so he's very easy to recognize. And then there is a server on the other side, and there is also an IP on this side, and a port through which the calls are going to enter. So what you do is you send, you assign a port, you send a request to this guy through the network, essentially through servers, and then he gets the request, assign a port, and send back the information. In all this sending forward and backward information, everything gets registered. Okay, so that's important because that's the origin of the data that I want to show you. Well, how do we get this data? Well, I mean, that means that you have to actually get some kind of agreement with a provider, which are the ones that are in the middle. I have got access to two databases of this kind. In the one case, the two cases were related to academic institutions, which were the middleman, if you want. So they are the ones that have the servers and can get this data, and in some cases are able to share that for research purposes. In one case, the set was all the web entering the web pages of the university. This was in Emory, in Atlanta. And in the second case, it was like this. It was in Indiana University. And what we did was actually the other way around. So we monitor a small dormitory in the campus and how they access the outside world. Of course, to do that, you have to be very careful because you don't want to use the identity of the guy, so to reveal the identity of the guy. So there is all the privacy concerns about how to anonymize the database and which kind of things to show. But in theory, this is the way to get this information. And so, just to be a little more specific about what you get. For instance, usually you get IPs. IPs are this kind of numbers here. But probably if you have been working with computers, sometimes you can see this kind of very long string of numbers. this identifies each computer in a single way, but some of them are dynamic. So some servers can actually assign different IPs among them. So that's something that's, it's good to identify single users up to a certain point. There have some limitations in that sense, okay? So, I will show you some data based on this, and of course there is some limits to what we are able to extract on that. The data in the second set of data, the data in Bloomington, in which we monitor the dorm, is at the base of MAC addresses. So MAC addresses are usually this kind of codes up here, and these are something that are assigned in a unique way also to computers. So in that case, you can really know if the computer connects or not to the network. These are, all of these can be changed. Of course, if someone wants to change and to mask their presence in the web, is able to do that, but it's much harder. Supposedly it's harder than likely that it's something that happens automatically. Okay? And then when in the data that I'm going to show you that we are trying to identify single users, we are talking of this market, not of the open. But okay, let's go why. The reasons why to do this and why to show this kind of things. So you can say, okay, well, the reason is to know if something like this is happening. Well, yes or not. That depends. No, usually no. Some people is doing that, and these people is doing this with these guys. So it may look like funny, but these guys are using that. So and that information without our with our permission in a kind of inconscious way, because they ask permission to use their tools, and then you give them all the information for free, and so they use them for their own purposes. We are not interested in so much, so we don't want to really compete with them, but we wanted to know if there is some rules on how people navigate and access the information. But of course there is this part too, and this, especially for data coming from the US, is very important. Also here, the laws in Europe are really sometimes draconian about the privacy concern, but in the US they are not only the laws, but also the people is very aware of the situation. So, we clean everything. We don't keep IPs or MAC addresses. And we essentially assign IDs to the people because we are not interested if A has been accessing this thing with the name of A. We are only interested in saying that one user has done this, but we are not interested in who is this user. So the providers sometimes clean this for us. They assign unique IDs. In other cases, it is ourselves doing this, and then there are all sorts of non-disclosure agreements and destroying the data afterwards. Okay. So just to make sure, I have to add this because I presented this on some other places where this thing of the privacy was very important, and then they always jump into the chat when you say, no, I'm going to look what the people look at in the internet. Well, yeah. No, we are aware of that, so we take care of this, and this is mostly what I was saying here. No? So the idea is that we want to see how people navigate, to track the navigation, but not really. We are not going to really use information about that people, just that they are seeing individuals. Okay, so that's the thing. And our final aim is actually to characterize the navigation patterns, to produce laws or statistical features that will be able to become the basis of models of navigation, of realistic models of navigation. Realistic in the sense that they are based on things or features that are found in the real world. And then we use part of the real data to validate that. Okay, so as I was telling you, the databases are coming from 2 points. One in Bloomington, which is here, and one in Atlanta, down here. They are very different places, even though, of course, everything comes from universities. But the difference is that Bloomington has 70,000 people. It's probably something is interested in that. It's a student city. It's the city of the University of Indiana, the public University of Indiana. Out of the 70,000, 50,000 are students. So this city is very interesting during the academic year, and the summer is kind of boring. but for the rest of the time it's okay. Atlanta is very different. Atlanta is the size of Madrid. It has 5 million people. It's a huge metropolitan area, and the data comes from Emory University, which is a small private university, you can see here, with 12,000 students and 3,000 faculty members. What we have is the access from outside to the web pages of the university. Well, I mean, this is just for people that has been in Bloomington or is going to be. This is the kind of weather that you find there. So, okay. This is also the kind of weather you find in Atlanta. The Bloomington, I mean, the Indiana University is much bigger. It has 50,000 students. This may be older, and then there's more than 5,000 professors and staff. Okay, so as I was telling you, the database in Emory is from outside to the university, and we have it for almost a year. So it's this 41 weeks in 2006. So we get register of every single click. Well, in theory, this is what they told us. Every single click from outside to the inside of the university. And well, I mean, when the IT service told us that they will be willing to give us this kind of data, I was worried in the sense that okay, the university is small, so how many book pages you can have inside? No? Well, when you start to look at the numbers, they are not so small. So the number of people that access the pages, different IPs. In this case, people means always IPs. Is 3 million in these 41 weeks. And the number of pages that they access, different HTML, HTML, PDF pages, because those are and PHP, I think. These are the only ones that we consider because there are all the things that you usually get, like figures or images that are embedded inside the pages, are like 2.5 million. So there are a lot of pages in there. So essentially what you have is all the pages of the administrative service, of the sports service, of the professors, personal pages of the students, and so on. And this is in a kind of hierarchical tree structure where each of them link to the next ones, and then there are like links together. So there are a lot of links and a lot of pages.
Excuse me, the IP is also from inside the university?
No, this is from outside to the inside of the university. Emory is always from outside to inside. And this is the number of clicks. It's 53 million in the time that we were observing the.
Are there routers on these university sites? Or?
They have routers, but the thing is that all the traffic from our site is centralized in a single place. So they have the logs. They have the logs of this big server of the university. Yeah.
So this number of URLs, these are only internal?
Internal, yes.
What kind of URLs are those? It's a very big number, 2.5 million.
Yes, no, this is what I was telling you. So they are only HTMLs, different HTMLs, different PHPs, different PDFs. But nothing else. I mean, we are not adding things like GPGs or
what kind of entity of university?
of everybody in the university. So it can be students, different departments, different professors. I was also surprised by the.
No, but this number is the aggregate, because if you calculate the average number of URL introduced per day, 8,000 times
this is
300 is 2 million. So that means that 2 days, just putting the same address, is telling you 2, no 1.
No.
But otherwise you don't get that. Because 8,000 times 300 is 24. So 2,400,000.
Which one you say? This one's 8,000?
Yeah, if every day is 8,000.
It was almost a year. So
300. 300 times 8,000. This is 2 million and a half.
Yeah, you're right.
I present.
But introduced per day in really new ones. I don't think.
Well, I mean, it is different in the full database. But these numbers probably are calculated.
No, but I understand introduced per day by users accessing.
Yes, different ones. That's what we mean here by introduced per day. So new URLs in the sense that they are different from the ones that we observed.
From the day before?
No, in the whole time before. No, so what we wanted to know here is, as we were discussing before about Bayesian models, how many things, new things enter into the network every day. No? So I think that this was measured like that. So total number divided by this.
So just to
but I will show you now how it goes day by day. Yes.
what information it is. So this is in inward and outward traffic, right?
This is
so also members of the university who serve to a certain site outside. So all URLs.
No. This is IPs from anywhere, including internal to the university, accessing the web pages of the university. So
only accessing the external.
This data, all the other database that I'm going to show you now, that has the other way.
But this is not possible that there are 2.5 million pages in the university. I mean, you showed that there's 10,000 students there?
There are 12,000 students. Yes.
Okay, so, come on.
You have a site?
One.
Yes, how many different levels do you have into the site? Or you have only one page?
For sure, not more than 100.
I have only one. But not for sure, not 500 exactly.
Well, I mean, you know that you're a normal user. I imagine they have 10 or 12.
Well, then this is not 500.
Yes, but I think that this is also this includes also things like databases of the different services. So there can be thousands of HTMLs in that. Okay, it's not, I mean, the users,
each single file.
the users in the sense of traffic are usually mostly normal people, but the users in the sense of creating HTMLs is not only user normal.
Well, also you said you count PDF files as a URL.
Yeah, PDFs.
So in university you get.
This doesn't make any sense.
Well, I mean, we want to know how the people look at that. That's the way we can. Well, but let's go to the next one because there are more things. We lose in the details. So the other database is the opposite of what Ingo was saying before. No? So this is from Blooming to Commuter, and in that what we are looking is one dorm, 1,000 people, and then what they are looking outside. Outside means anywhere outside in the outside world. So it can be in the university or outside the university. Okay. So and for that we have this is a little more than a month, so it's the period of time is smaller. But well, the HTTP, so the number of URLs, because this would be URLs requested, is much bigger, and then the number of clicks and things like that is higher. So the number of different MAC addresses, just to give you an idea, is this 1,083, which is more than the number of students in the place. So that means that some of them have two computers, but not so many.
Can you explain the difference between HTTP requests and page requests?
What is it? Page request? Well, one of them may be related to the domains, but I cannot tell you what is exactly the difference. To the domains or to the clicks? No, these are the clicks. So these are all the requests from there to pages. These are the different pages that.
So it's in total about 30 million different.
Okay, so
everything is persons? It's not robots or anything?
In this data, yes. In the one in memory, no. And actually, we managed to see these are the differences.
Okay, that means almost 1,000 clicks per day per person.
Yeah. But I mean, clicks. No. Clicks many times means that there are automatic things inside one page. I mean, when you go to one page, you can get access to many things that you are not knowing, and there are many automatic processes in there. In this case, I think that this is not clean in the way that we did it. This is just a request in a while way to anything that is. Okay, but then the question is, let's go back to memory data. I'm going to show you some results on that. No? So these are, remember, everything from outside or even the university to the server of the university. No? So pages in the university. And what we have here is the clicks per day that we were observing in all the database, which is this 40-something clicks. And we saw, the first thing that we saw with this clicks per, I mean the average was the total clicks per day that we were observing, and doing these kind of things. So I imagine that everybody can have an idea of what is happening here. No? So you have a very clear oscillation. And if you count the points, you realize that it's 7. The number of points of the oscillation, so there is a circadian rhythm in both in these things. And then there were two very particular things where people...
Where's the maximum, where's the minimum?
Well, I mean, that's too much. Yes, there is another longer period here, but I don't know. It can be 6 months. thing. There are two very particular periods of time here, which very highly frenetic activity, especially this one. And this is the beginning and the end of the semester. So professors put, or professors of everything in general, the people of the university put new content that generates more activity. And for instance, the kind of content that is generated here is the final exams. So this is the 24th of December, and this is the date in which the final results are put online, all of them at the same time in the same day. And that generates a lot of traffic actually in the university. Much more organized than the other one, which is the beginning of the activities. That's important for something that I'm going to show you later. But I mean, just let's go on with the simple analysis of the data now. This is all aggregated data, no? So we are not making. I mean, I know that we derive the data on the IP level, so we can say that there are single users, but still we are not really exploiting this fact. Everything is aggregated, so we are just adding stuff. And what we see is for a weak data, so if we make a sum of the previous curve that I was showing you, in one of these oscillations, you will get this kind of curve here. Then, I mean, with the error bars, no, which are 1 sigma, I think, in this case. Just to give an idea of which are the fluctuations on this user week. One of the things that you see is that, for instance, this is Mondays. No, this is Tuesdays, Wednesdays, and so on. This is Mondays. So the activity. Remember that these are pages in a university. The activity should be related to work somehow, or studies, and still the activity is quite low in Mondays, almost as low as Saturdays, which is a very peculiar thing. No? So, and then, just out of curiosity, we look at what happens in a very strange week, which is the one that is marked in black here. Here, this is the week of Thanksgiving, which is a major holiday in the US, where everybody tries to travel home and visit the family and so on. So, and what happens is that the holiday is from Thursday to Sunday, which is the moment in which everybody is traveling. And what you see in this week is that actually the activity the Monday before is quite low. Actually, like people is already knowing that they are going to go on vacation. Then Tuesday, the activity gets higher than the usual one. And then, of course, it decays during the holidays. And then on the next Monday, it's still lower than the usual Mondays. And then it goes back up. So this week is actually very peculiar in this sense. Then we can do that even hour by hour in a higher level of resolution. So what I am showing you here is the black curves is the typical day of the week, so weekdays, days where people is working. And you have this kind of shape. These are the hours, so 6 a.m. So the curiosity is that actually you have, this is something that you can expect, that there is this hole here, which is just in the lunchtime, the usual lunchtime in the US. The Spanish one will be immediately to this side, to the right. Then when people comes out for lunch with more energy to click or to look at the news, I don't know. And then this decreases quite fast for around 5 p.m. where students and probably staff members goes out of the university. Then there is this kind of plateau until 10 p.m. that you can probably guess who is doing this. And then it goes on just for the night. Saturdays are the red one is the red curve is only for Saturdays, and you see that actually the shape is still reproduced. So somehow the activity during Saturday is mimicking part of what is happening in a workday. But I mean, the activity level is lower, several orders of magnitude, but still the people that is there is doing the same kind of things. Then what is very different is of course Sundays, which is this flat curve in blue here. So these are the kind, if you want, the kind of information that you can get with this. No? So information about how people, I mean, the kind of activity that people develop. Then well, this is a little boring stuff. This is one because in the sense that this is the usual power laws that you find everywhere. But these are quite good power laws for what they are. So these are the distribution of the number of requests, and as you see, it's a long power law with this exponent. But finding power laws in
number of requests,
number of requests means number of clicks. So IPs per IPs.
What was it? I didn't get what it was. Let you go back.
This is
what it was.
So this will be the number of requests per user.
In which period? In what?
In the full database.
The worst per user.
Yes. And then you get this looking thing. So number of clicks per user if you want.
But you have
Over the
some,
whole period.
Over the whole period, yes.
you have some which is clicking the median.
Because here there is automatic things inside. So this is the way to, I mean, one this could be the, you want the natural way to distinguish them is say, okay, you see, you can click so much in a person. The funny thing is that actually statistics doesn't, well, there is some change here, but it's actually not so far away from what should be in the rest. There are other ways to distinguish them, more than other things, because they are, most of them they are periodic. So they have a clear cadence. But okay, I don't know if I have, well, let's see if I have something about that, otherwise I will tell you something about this point. This is the number of IPs that enter into a single page, so and again the distribution. And this is the time between visits, and this is the very true question. So we have the IPs, and still the users, they'll say identified by IPs, and the web pages, no? Like these URLs. And what you look here is the period of time in seconds that goes between one visit and the next one of the same user to the same web page. Okay? And we're finding this thing. There are some peaks, and I have to warn you, this is due to the 1 day, 2 day, 3 days periods. And so actually, if you look at this in a zoom, you will see the oscillations, and this is just the cover of the full curve, because this is done in a log medium scale. So you are seeing only the main component of the full curve, but there is like oscillations here, and this first peak corresponds to 1 day. Okay, 24 hours. Well, the envelope curve goes like t to tau to the -1, and this was corresponding to what a model of the time was saying, which was the Barabas's model of human activity. That essentially is a kind of queuing model. And I'm going to talk to you more about that because of the next result. The next result is users to the full domain of the university. No? So we have a single IP, and we see how long it takes for him to go back to the web pages of the university. So he entered one, we look how long it takes to go back to any page in the university, doesn't matter which one, and then to the next one, and so on. So these intervals of time are measured, and we make the statistics. And you get this, again, this very long curve with a lot of scales here, well, decades here. The thing is that this doesn't correspond to -1, which is what the Barabas model was predicting. And we were trying to understand what was happening. Actually, you can modify slightly Barabas' model, and you get this kind of behavior. And the slight modification was, you want almost trivial in the sense that the Barabas' model is based in a queue. So the idea is that people establish priorities to the things that you want to do. So imagine that you have a certain vector, which is a certain box where you are going to put the task that you have to do. And you assign to the task a certain priority, which in that model, since it's a simple thing, is just a random number between 0 and 1. You essentially execute the task with the highest priority. You order them, and just take the one with the highest priority, and execute it. And in the original model, you have to add a small, slight probability of choosing any of the orders, because otherwise the thing doesn't work. But if you do all this, the period of times that the task remain in the box follow this 1/tau distribution. Okay? So this is the idea in the model. It's just that people have some kind of priorities, and from time to time they do something that doesn't correspond to the priority task. What you have to do to change this is to take into account that actually, when you are talking about clicking pages in the university, you are not only clicking one. I mean, usually you go there, look at one page, but most commonly you enter in the page of the department and go to the page of the professor, and then for the page of the course that you are following. So there are like 2-3 clicks in a row that are strongly correlated, so the events, I mean, the interval between them will be very short. And also, I mean, they are chosen also as priority tasks, the 3 or the 4 of them. So what we did to modify the model was just to add this possibility of executing more than one at the same time, all of them chosen with the same criteria. So priority or random, depending on what you do. And if you do that, what comes out is this 125 exponent, and it regardless of the number of threads that you execute, if there are more than 2. That's the only condition. So okay, this was a nice thing, because this is what we were finding also here. And if one is an indirect, let's say, evidence that talks about something, some mechanism of priority is actually down there, which is also in discussion, because there are a lot of people that don't believe in this priority tasking explanation. But okay, this was an indirect test of that. Then we went. One of the big discussions that I got when I saw this kind of results in a conference was that, but the users, you are mixing all the users in a single box and making the distribution of inter-event times, but you may have users that are very active and then some others that never do too many clicks. So how this affects to the power load that you are getting, and is it not actually influenced by this traffic in the users? Well, yes, it is influenced, but not as much as they were expecting, because they were actually thinking that the users were doing something in a Poissonian way with inter-event times that were distributed exponentially. That's not true. That's not true, categorically, because with the new data in Bloomington, we were able to test that. Since we were able to identify single users, when you do this kind of distributions for single users, here you have 4 of them. What you get is this. So the exponent is different, it's true. Well, remember here we have single users to the outside world, so there can be many things in the atmosphere. But still, this is a very long tail distributions, and very different from exponential in the inter-event time behavior. Okay, so I am starting already to talk about the other data in Bloomington. Just to tell you, we measure all this automatically, of course, after a while, because we could not measure the 1,000 users by hand. And this is the curve that we get for the exponents in these values. It's like it's like a Gaussian-like thing. It's centered around this 1.50 something. So still, these are relatively typical values of that. Okay. And then the other question is that starting to talk about already about the Bloomington data, where I was telling you, we are able to actually follow every single MAC address and where we go. And this is because we were interested in to actually see the navigation pattern. So not only the full population statistics or properties, but what they are doing. And to do that, I'm going to show you this kind of plots all the time, because this corresponds to what we define as sessions, which is every single node or ball here corresponds to a web page, and then the users are just navigating with the hyperlinks through them. And what we register is this kind of chain of events, and then we see that he's looking at this. We know that there is a link here because there is an origin and target of the request. So we know that this has been following the link of the page. And then we see all of a sudden that he started in origin request again from here. So that means that actually he clicked probably the back button into the browser. That's something that doesn't keep registered anywhere. Because when you are navigating, you click the back, the page is usually in the memory of the computer, and there is no request to the outside world. So there is no way to register that movement. We do it because we assume that if the next request has as origin one of the previous pages, he has one back. So this is is a way to construct these navigation patterns in a way that that allows us to treat these structures. Because the kind of things that you get here are essentially trees, and the trees there are several tools, standard tools to study and analyze them. Okay, so the other one was a very simple navigation tree, but there are these much more complicated navigation trees. All of them, these are done by users, and these are for sure human users, not like the ones in memory which were missing to them. And okay, so the question is that we got these trees. We can characterize them by the number of levels that we have, by the number of pages visited in every single session. We consider a session a moment in which we see as origin of a request something that is not in the previous history. So when we see that the navigation has disconnected, that means for us that the user has started a new session. And so each of these trees will represent a session in navigation. So a kind of thing that has been a chain of events connected one to the other in a kind of causalistic, well, at least orderly. So the question is how to model this kind of things, and if we are able to recover or not all the properties that they have been showing you. So those referring to traffic in the web pages, to number of pages visited by the users, to traffic on the hyperlinks, or even this kind of more deep structures that characterize the trees of the navigation. And well, the first model proposed by to do this is one that I don't know if you have heard about, PageRank. It's the one that in which Google is based. So it's a quite old idea. So the question here is that well, I mean, of course, the creators of Google didn't settle this idea. It was a different algorithm. But it's equivalent to this. So it's equivalent to have users that are navigated randomly on the web. And then they just go following the hyperlinks for a while, and there is a constant probability of, at a certain point, saying, okay, I'm finished this session, and I'm just a part of this, and I start a new session somewhere else. No? So this is the kind of model that actually generates a certain popularity of the page on the pages based on the number of users that fall into that. And this is essentially what PageRank usually do. You order the pages by the number of users that fall into that. So you join the content that the user, for instance, this is how Google used to work. You join the popularity of the pages, so the number of users that it should be attracting, or at least users with this random work, with the content, and that's what gives you, which is the order in Google at the beginning, and it's now it has growing complexity, so it's you have to do. This a probability of starting a new session is called teleportation in the environment, and these are very important because for us this is what originates a new session. No? So these trees that I was showing you will correspond to everything that happens between these two teleportation events. So this is navigation trees. Okay, so we propose refinement of this because, and as I will show you now, this was necessary to explain what we were finding in the data. The refinement is that actually the users are not just starting anywhere in the web, but usually they tend to start mostly in certain sites which are related to what they have in the home address or in the bookmarks. So this is the reason why this model was called PageRank, because in all the rest is exactly the same as the previous one, but we are keeping a set of pages that the user has visited. It can be all the set of pages, and then choosing the one is going to start from proportionally to the rank they occupy and the number of times the user actually visited them. So we just keep a rank based on how many times someone has been there, and then choose the page to start based on this rank using power law, because this was measured actually in empirical data before. There was some papers actually talking about this. Then we added some more thing, which is this back button, because we wanted to explain also this thing that you see sometimes, that you see some people coming back into the tree and then going back down. So we added that as a parameter, but that's measured key from the data. We know how many times this has happened, and this is the key that's going to the back button. Okay, so with this model already was able, and I will show you now, to reproduce some of the features of the empirical data, but not all. And those that was not able to reproduce are the depth of the sessions. So essentially are all related to single sessions. The problem here is that if you have a certain constant probability of starting a new session, that means that the size of the sessions that you will observe is exponentially distributed. And the empirical data don't have that. So the empirical data actually has a long tail distribution in the session size by single users. And so we have to add something else. And this something else is related to the interest that the users keep. So when they start to navigate, you start to find things that interest you, it's more likely that you go on that. So the model that we introduced is this ABC, which comes from agents, bookmarks, and clicks, which is essentially an agent-based model in which each agent that is navigating follows the rules that we were discussing before, except for the one of the probability of starting a new session. For that, he has a new variable that is called, we call it interest, that it can be either energy or whatever. And then this variable is doing a different random walk, and when it just touches 0, then the session stops. Okay? So this is the complication that this model has. So these are the 3 levels of models that I was telling you at the beginning. And this was necessary because of this. No? So because of the traffic, this is the data about traffic on the, I think this is on the web pages, but yes, this is on the web pages. No? So PageRank is the blue curve here, and as you see, PageRank, I mean, the random walks in general actually define a popularity for the pages, which is based on the topological structure of the network. So if you have a network, like by default is already scale-free, so you will find a popularity that is distributed like that. No? And this is what you are seeing here. I mean, this curve is a long tail curve. In this case, it was not following very well the empirical data, but sometimes, I mean, you have to overscale the things and take into account that, for instance, these ones, these sort of things here are missing. You can get a relatively good fit to empirical data. The other models, of course, are doing that too, because they are more complicated, so that's by default. Now, the problem with them is, and of course, let's say the ABC is also doing that. Just a comment here. We use this to actually estimate the parameters that were missing in the other models. Not for PageRank, because that's a very easy thing. I mean, we are just keeping the list of pages visited and then selecting them. So in that, there are not so many parameters. In the other one, there is all the parameters associated with the energy. And then we are extracting those parameters from fitting these curves, okay? The ones about traffic. This is because all the models, I mean, PageRank is able to fit the traffic on the pages, but it has a lot of problems when you look at the traffic on the hyperlinks. No? So that's the difference with of the 3 models. The second model was proposed because of this, because actually there was something missing. And it is that since PageRank is based on random walks, so every user chooses a page of random to go on, what happens is that actually the distribution of traffic on the hyperlinks, on the links, is following this kind of curve, which is very central-like, so it's a kind of Gaussian. In the real data, with these black points, actually the thing is much long tail. And to be able to explain that, actually PageRank was able to do that qualitatively, because it's not fitting exactly this one, but at least the trend of the simulation seems to be going into the right direction.
Yes, what is the omega again? What is omega here?
Omega here is the traffic on the hyperlinks, on the connections. Okay, so the problem with let's say, of the 3 models that I showed you, PageRank is able to reproduce the traffic on the pages. It has problems with the traffic here, the traffic on the hyperlinks. And then the page, what we did to the bulk rank, so the one in which you have actual memory of where you have been before, is able to reproduce the traffic on the hyperlinks. But, and of course, the most complicated one too, and actually, as I was telling you, this is fit to reproduce this. But it fails here. Because the 2 preferred models, so PageRank and the second one, have this constant probability of stopping a session. And so the trees that you see are all in size distributed in an exponential. So you are usually seeing very small navigation sessions, and we are seeing long, deep ones in the real data. So we have to introduce a more complicated model to explain these ones. The more complicated model, the ABC model, is fit to the traffic. So the parameters are fit to the traffic data, and then we are going to compare the results on the sessions. Okay. Which would be essentially what was the aim of introducing this more complicated, the third more complicated model, let's say, into this. So what you are seeing here is these are how the other models fail. No? So careful, because here the empirical data is in a curve. It's not the points anymore. But this is for these trees. This is the depth. So essentially the number of levels that you have into the tree distribution. So as you see, the empirical data has a relatively long tail, while the other 2 models, so the PageRank and PageRank, so it's the first 2 models, are producing this exponentially distributed thing. So default very fast into the thing, and they are out of range into the data. Here, the same happens with the total number of pages visited per session, which is this curve here. Again, the curve is the empirical data, and the 2 points, I don't know if you can see, but there are also squares. So they correspond to the 2 types of models. I'll give you explanation as curves. So this is the reason why we introduced the last data, the last model, and it is because actually something like that is able to reproduce at least qualitatively unique, because this is quite hard to, this is real data, so really fit that, or you fit it, or then just forget, but if you fit it, you are not producing anything new. So remember that this model is fit to the traffic data, to the complex traffic data, not to the sessions. So the comparison here of the sessions is based just on the model on empirical networks that we found, and it's simulated on top of these empirical networks, and we compare the sessions that we find in the model and the sessions that we find in the empirical data. Okay. So again, the empirical data is this continuous curves that has as many points as this, because the points are just discrete, so they are not too much. And then the points here correspond to the model running on the different sets of web network that we have been analyzing. So we got a couple of them actually. I think one is from the UK, and the other, if I remember correctly, was from the US, but it doesn't matter. It's just big chunks of the web with hundreds of millions of pages connected with the hyperlinks, and we ran the model on that to make it more realistic. Because actually the results depend a lot on the topology of the object where the users are moving. So, and well, I mean, again, the book rank, so the scores are still here just for comparison. And as you see, the last model is able to actually mimic that without fitting the results. And so this is essentially what I wanted to tell you here. So we have constructed these web navigation traces, and I studied them empirically, which is something good because there's something to be done. So just to characterize them, we have been extracting some features out of that we wanted to implement into models, and this has produced this kind of family of models, more complicated models. One, of course, was already there. PageRank was already proposed in the 90s something, but I mean ours have come afterwards just to try to explain what we were observing into the traffic thing. So we are going deeper and deeper into the characteristics of the user navigations, and well, I mean the question is, my idea would be actually to continue that, because the navigation is based on things that this model is not taking into account. The interest variable is just a very rough approximation to the reality. I mean, in reality, probably navigation is attached to content, and that's something that actually should be necessary in an empirical way, and also put into models if you want really to model how people navigate the web. And that's probably something important. If you someday in a crazy world will you want to predict what will happen with the pages that are introduced, or whatever that you put into that, or I don't know, some kind of strange situations when the web was crazy for some reason or another. So this kind of models will actually, if you are able to produce something that realistically tells you how the traffic will behave, you will be able to say something about how the thing evolves under certain circumstances. So, and this is essentially what is missing, and probably will work for the future. So that was it. Thank you very much for the attention.
So, I think there is time for one.
I will just show you this. So my collaborators on all this, and especially the papers, there is one more. Okay.
There is time for one question. So have you tried, with the memory data, you could really track how people browse the web pages there.
Yes.
So whether you, when you enter one page, most of them follow this link and not the others, and look into this kind of thing.
Yes.
So,
well, we don't have in that case. It was actually like, for instance, when you are trying to do the full model navigation, you need the hyperlink network. And then that's something that we don't have currently. Even we don't have in the content because this was in 2006. Everything has changed quite fast since then. But you can at least say this is the region and the target of the team. Yes.
Well, at least aggregating data.
Yeah.
But I suppose that in that case there are patterns of activity. I mean, that you have 5 links. It's not that, well, some of them follow one, two, but probably there is most of them follow one of the path.
Yeah.
And that's probably not, I don't know how good the model you are proposing is able to capture these patterns.
Well, I mean, this is something that was already happening with the PageRank because, I mean, if you want, it's produced naturally if the users start mostly from the same position. So that's essentially increase the traffic of the links going out of this page. So if everybody is entering, I don't know, the main site of
but there is due to the topology, but I'm talking more about the content, right? So you start reading the news by the international section, then you move to the national.
Yeah. No, I mean, that's the thing
the
thing that is missing somehow is that also is you think, for instance, all the links that are in the Paris page or Mundo or whatever newspaper will be very big compared with the links that are in my page, for instance, that not so many people visit. So already you have this kind of control of a starting point effect. The second one is, as you were saying, is what happens within the links of the same page. Why people choose one over the other. That's not still in this moment. This is based on content, probably. So how people actually choose one or the other. And that's what is missing in this things. So that would be good to go.
Okay, so, well, he will be here around, so you have any question or want to talk with him, you know how to find him.
Okay.
Thanks.
Thank you.